How's everyone? Doing all right? I promised myself that I wouldn't say anything about the Cowboys. But I guess I just did, didn't I? You were so glad? Oh,
It doesn't even bother me because we're still in first place.
I know. It's pretty sad, isn't it? I almost got jumped at HEB because I was watching it on their little big screen. And I was all cheering whenever Detroit scored. And I realized there's a bunch of Cowboys fans around me. Yeah, it's all right.
All I gotta say is Calvin Johnson is an animal. 329 yards receiving.
Yeah, it was pretty impressive. Okay, so questions over homework. I asked you to graph those functions. Pretty straightforward. Okay, then let's just pick up with today's material. So last class we defined an exponential function to be something like this. F of x equals b raised to the x. We had some restrictions. B had to be greater than 0. B could not be 1. Right? That's what we had?
Yes.
And we call b the base of the exponential function, right? And we looked at a couple of them. We looked at like 2 to the x, 3 to the x, I think 1/2 to the x, right? So what we're going to do now is take a look at two pretty special bases, all right? So I'm going to put this here, two special exponential functions. All right, the first one is the base 10 exponential function. And that would mean your base is 10, right? So f of x equals 10 to the x. So as you start plugging numbers in here, you know, you plug in some nice numbers like 0, 1, 2, 3. Those are just powers of 10, aren't they? Yes? And then if you plug in negative numbers, you get 1 over 10, 1 over 100, right? You could make the table for this. And base 10 is what our number system is, right? Our number system is base 10. So this comes up a lot later on in other math courses. So I just want to make a note here that the base 10 function, exponential function, is one of the two special ones. The other one is usually the one that confuses people. It's the base e exponential function. And it's f of x equals e to the x. Now, I need to discuss with you what e is. Now, to do that, I think what I'll do is I'll start with a number that a lot of you are familiar with. Y'all ever heard of pi before? Right? Pi is approximately 3.14, right? You've heard that before? And it has to do with circles, right? The pi is somehow, you can use pi to compute the area of a circle. You can also use it to compute the diameter or circumference. So it's used a lot in geometry. But it's a very special number in math, and anytime we have a very, very special number, we usually represent it with a letter. Now, pi is a Greek letter. Okay, so now something about this 3.14, it actually, pi, if you were to try and write it out, you can't write it exactly. Like you can't go 3.14. It's not equal to 3.14. It keeps going forever. It's the next digit's 1, then 5, and then it keeps going. And the thing about pi is that it never stops and it never repeats. So it's not like the number 1/3. 1/3 is 0.333, but it keeps repeating, right? So it's not like that because it doesn't repeat itself. Does that make sense? And it's not like this one either. If I had a decimal like 0.252525, that again repeats itself, keeps going, repeats 252525. You can't get any pattern out of pi. That's what kind of makes it special. And so any number that has that keeps going forever and never repeats itself is called an irrational number. That's what we call them. So that's pi. We're all kind of familiar with it. E is an irrational number also. And E is approximately 2.718. And you probably remember that from your homework, right? So 2.718 is about what E is. Now, I can't write down E because it goes forever. It never stops. It doesn't have a pattern. So it's such a special number in math that we give it a letter. And the letter we give it is E. All right? Y'all okay with that? Now, E is used in calculus a lot. So it's going to be kind of tough for me to explain why it's so important. You'll just have to kind of trust that it is at this point. But all we need to be able to do is graph it, which you already did for your homework. But now I want to make you aware of a key on your calculator. Everyone should have an E key. All right, so I want you to try on your calculator to find your E key. I thought about giving a quiz today on whether or not you have your calculator. Would you all like that quiz today? 100 if you have a quiz or have a calculator, and a 0 if you don't. Now your phone doesn't count, right? Yeah, and you can't have pink calculator. Sorry, that's the rule. This is college algebra. I'm just kidding. Okay, so everyone find their key. Now here's what I want you to do. I want you to try this on your calculator. Let's go ahead and try and create the table for e to the x. Now, I do not want you to do the 2.718 because you did that for homework. I want to see if you can use that e key. So you're going to have here x, here's e to the x. Try and plug in -2, -1, 0, 1, and 2. And you should get answers pretty close to what you got at home for the 2.718. But use your e key. Everyone's calculator is different, all right? So let's see if you can do this. And then let's round it maybe 2 decimals. Or we'll say 3. We'll say 3. Now, what I do need to see is someone who has their calculator but can't find or can't figure out how to use their E key. Raise your hand, I'll come by and help you real quick. Everyone else? It's okay? You got it? There's 2 different ways. You have to be kind of careful. Yeah, that's right. Anyone else? That's why. Sorry. It's not scientific. That's clear everything. That won't work. Anyone else? Okay. Let me see. You turn on the lights. Okay, your E key is kind of tough. All right. So the way your calculator works different than some of the others. What you have to do is you have to type in this number first. Okay, so if you want to do E to the second power, first type 2 in. And then do your second E. Okay? You got yours okay? No? I didn't say there it is. Okay. We should all get the same answer. Okay, yours actually is very cool. You see this thing search all. Get to this second key first. And it brings up the menus. All right. I know what to do. Then you hit to the right. Number 2. Number 2 is up. Okay, now put it in. Okay, so you might want to case you forget how to get there. Anyone else? Yeah, just round it 3 decimals. Yeah. Round your answer 3 decimals. So everyone's good, right? No, no issues. This is important because every one of you has a different calculator, so the way you type it in is different. And you don't want to get to the test, the day of the test, and then that be the first time you're trying to do any of this stuff. All right? So make sure you're okay with this. Let's finish this out. What was the next one? Who wants to tell me what e to the negative 1 was? 0.37. E to the 0 is 1. E to the 1 is 2.72. And then e squared was 7.38, something like that. Okay. But you now need to make sure that you're okay with that E button, all right? All right, that's pretty much it, okay? Those are the 2 special ones. So the base E exponential function and the base 10. Now, I want to talk a little bit about transformations. Do you remember, it was quite a while ago that we had those toolbox functions, and then we moved them up and down, left and right, flipped them over. Remember that stuff? Shifting up and down, left and right, yeah? Reflections over the x-axis, reflections over the y-axis, that sort of thing. We can do all those same things with exponential functions. We can move them up, down, left, right, flip them. Okay, so let's do some practicing on that. Before I begin, though, I will remind you, just briefly, remember, this is what a function, an exponential function, looked like, right? If b was what? Maybe if I put the other one up here, you'll see what I mean. This is what it looked like if b was something else. It went the other way. Well, that's true, but that's not quite enough. Because b always has to be positive. The base, yes. Which type of base would we need to get something on the left? Which type of base? Not 0. Greater than 1. Okay, so remember this over here. If b was greater than 1, this is what happened. It was, we called it exponential growth. If b was what? It was this one. Less than 1, but of course, b always has to be greater than 0. So it turned out like if b was a fraction, like 1/2, we had decay, right? This was decay. And this one over here was growth. Because you read graphs like you read a book, left to right. So if it goes up, it's growth. If it goes down, it's decay. Right? Remember that? Okay. So we know just by looking at exponential functions, if we know the base, we kind of already know the general characteristic, the general behavior. Now it's just going to be a matter of moving that thing up, down, left, right. Flipping. Yeah, that's right. I should have put those on here. We had that horizontal asymptote. And on this side, it would be on the right side. Yes? We also had this point. Remember that point right there? That was always 0, 1, right? That point right through the y, our y-intercept was always going to be at 1. Okay, using that information right there, let's try and do some transformations. So let's just move these things around. Ready? Okay, here we go. First example. Let's sketch f of x equals 2 to the x plus 3 minus 4. Now I'm jumping right into this, all right? So I'm not even building up slowly here. It's just, here we go. So what I want you to realize first is that the x plus 3 is in the exponent, isn't it? It's the power. So our variable is in the power. Our variable is in the exponent, which makes this an exponential function, right? What's the base of this exponential function? 2. All right, so our base is 2. And then we have this thing sticking out here on the side, this minus 4. That's going to be something. Well, let's kind of take it one piece at a time here. First, I know this. I'm just kind of thinking through this at this point. I know what 2 to the x looks like, don't I? What does 2 raised to the x look like? Is it growth or decay? It's growth. So I know that I have this. Now, I'm not even going to make a t-table. I'm just going to put this right here. That right there is 2 raised to the x. Do you all agree? Very rough sketch of what it should look like. Yes or no? Yes? Yes? Okay. Now, we have 2 things to look at now. We have the plus 3 up in the exponent, and we have the minus 4. The plus 3 does something to that graph, and the minus 4 does something. What do you think the plus 3 does? Would you think one of them is going to move it up and down, the other one's going to move it left and right? Okay. So remember always that the number that's outside by itself, separated from the function, which is this negative 4, is always your up-down. And the number that's up there in the exponent is always your left-right. If you want, you can go back to like one of the problems we did way back when, where we had like x minus 2 squared plus 3. This was a toolbox function, was a parabola. The minus 2 told us to go left or right, and then the plus 3 was up or down. It was kind of like this. Do y'all see the similarity? So here's what I've got. I've got the plus 3 up here, which is going to move me left or right. It's opposite. Remember, left-right shifts are always opposite of what you think? So this is actually going to move me left 3. And then the minus 4 does what? Down 4. And does it matter what order I do this? Yes, remember the order was always to start with where the x is first. So I would always do that plus 3 first and move my way out of the exponential function to the minus 4. So I will go left 3 first, and then I'll go down 4. That okay? So I need to take this blue function here, move the whole thing left 3. And notice I'm kind of making that point real apparent to you, that blue point. What would happen if I take that point and move it to the left 3? What would I get? What would my picture look like? So 1, 2, 3. It would be over here now, wouldn't it? And I'm going to do this one in green. And then other than that, I still have this, don't I? Then I need to move this down 4. So I'm going to say this right here is just the 2 to the x plus 3. That's just moving it to the left 3. Then moving the whole thing down 4 should just move everything down, right? Now, right now, the green one, did it change the horizontal asymptote? The green shift. No, everything moved to the left 3, but your horizontal just stayed. It's still there. But moving down 4 should move my horizontal down 4 also.
Moving down 4 is basically you're moving it down, but you're going to flip it too because you start having what's on that.
Well, you'll see where it is. Let me do this in a different color here. I'll do it in black. So I'm going down 1, 2, 3. Here's 4. Right? No, I went down 5, didn't I? 1, 2, 3, 4. I'm supposed to go down 4.
But you went down 4 from the original point though?
From this point right here. 1,
You went down 2.
2, 3, 4.
No, because that's at 2, not at 1.
What's at 2?
The green dot.
No, it's not. It's 1 unit high, remember? Remember the y-intercept was 1? Remember this was 1? Right? Because remember, 2 to 0 was what? 2 to 0 was 1. So that point's always 1 unit high. So I move it to the left 3, 1, 2, 3, and then when I go down 4, it's 1, 2, 3, 4. Do you all see that? There's the point. Now, where's my horizontal? It was right here, wasn't it? But now it's down 4 from there. So 1, 2, 3, and now it's down here, right? y'all see that? So my horizontal's like this. And so my graph should look like that. And we don't have to be real particular on that. Yes. But all the horizontal is affected by is an up-down. In this problem, the only thing that affects it is the up-down. That okay? Rough sketch?
So we're not worried about X and X and none of this.
Nope.
Move it to the
Nope.
left,
Move it
right.
to the left, down. Just shift it, draw it. Yep. That's all we want right now. Okay, let's try another one. How about this? F of x equals negative 1/3 to the x minus 1 plus 2. All right, so what type of function is this that I'm trying to sketch here?
That would be
It's exponential, right? Because my variable's up here in the exponent. The base is what? What's my base? What's the thing being raised to the power?
the base is negative.
Just the 1/3, not negative. That negative is outside, like a -1 sitting out in front. Okay, so this is like a -1 out here. The only thing being raised to the power is the 1/3, right? It's 1/3 raised to the x plus 1 because it's in parentheses. That okay? So tell me, is this exponential growth or decay? This is decay, right? Because 1/3, my base is smaller than 1. So here's what I can tell you so far. I know that this thing goes through 0, 1, but I know it decays. So it looks like this. That's what 1/3 to the x looks like. Agreed? Just 1/3 to the x. That's what it would be. Now I need to do my shifting. I'm going to do the x minus 1 now. What does that do for me? This right here moves me right 1. What else am I going to have to do? Up 2, but I'm going to leave a space here because there's something we missed. The -1 in front, right here, does a reflection over the x-axis. You'll have to recall that when you put a negative in front of your function, a negative out in front, that always reflects it over the x-axis. Do you remember that or not? Now that we've discussed it slightly? Okay, so what I have to do is I have to take that blue picture. I need to move it to the right 1. I need to reflect it over the x-axis, and then I need to move it up 2. In that order. So first, let me go right 1. If I go right 1, that's just here, right? And now I'm going to draw my graph. That did not affect my horizontal asymptote, did it? Nope. Now the tricky part, reflecting that over the x-axis. So what you're trying to do here is take this picture and reflect it like this. So do you see this? I like to just take this point here. That point's 1 unit, right? This one, the black point, is 1 unit high. I'm just going to move that down 1 unit down here. Right? It was up 1, now it's below 1. No, every point, whatever distance it is, bring it over to the other side. Every single point, bring it to the other side. Same distance. And what you get is something that looks like this. You see that? See that reflection? Actually, you know what? I don't like that. This point over here, well, no, that's right. Does that make sense? Come on. Are we done though? Up 2. Yeah, it's going to go back up to that black dot, right? But it's going to still be kind of upside down, right? And what's going to happen to my horizontal asymptote? That blue dotted line is going to go up 2 also, right? So let me do the blue dotted line first. It's going to go up, let's see, this would be 1. It's going to go up 2. So it's going to be up like this. This dot here, the green dot, is going to move up 1, 2, which is going to put it right there. Y'all see that it moved up 2? Y'all see that? This point, 1, 2, so it's there. This one up 1, 2, so it's there. And it still looks the same as the green one, right? Goes like this. So it needs to kind of flatten out towards my horizontal, and it needs to take off like this. So the red one is the answer. Do you think I don't know you're texting? So you know I know? Okay, I'm just wondering if you're trying to hide. Okay, so you know I know. Okay. I always wonder if people think that I don't know or something. Okay. I'm just curious, that's all.
So how do we know where the horizontal axis is?
From where it is. Okay. What's that? How do we know that it went up 2? Everything goes up 2. So when it said move your function up 2, then every characteristic of your graph goes up 2. So if you had a horizontal, no matter where it is, it will go up 2 also. Okay, so I'm taking all this stuff out of here. I mean, this is basically what we have. That's the exponential function. So you would almost even argue at this point that it's no longer exponential decay, is it? I mean, because we've done some stuff and now, yeah, it's a different kind of decay. So whenever we have just the base, like 1/3 to the x, yes, we can talk about growth and decay that way. But once we start moving things around and flipping and reflecting and stuff, it may look a lot different than what we think it does initially. Yeah, it's still getting closer to something as we move to the right. Okay, that good? That's all we're going to cover on transformations. Now, we get to logarithms. Logarithms. In my experience teaching this course for so many years, this is kind of where the wheels start to wobble a little bit, you know. People, you know, they look at logarithms and they automatically start shutting down because it's something that they don't have a lot of experience with. And so they're like, "Oh, this is why I hate math." It's a log that, you know, can move. Let me try and motivate what a logarithm is by doing something I hope seems reasonable to you, all right? Remember this? If I had a function like this, 3x, and we said, okay, look, we're going to take some numbers like 2 and 3, and let's send them through this function, what would they come out on the other side to be? If my function is 3x, I plug in 2, what does it spit out? 6. And what happens when I plug in 3? 9, right? So 2 went to 6, 3 went to 9. And then last couple of classes ago, we talked about going backwards, right? How could we go back and send them back to where they came from? We'd find their inverse, right? We'd find the inverse. And in this case, if we went through the process, we would discover that the inverse is 1/3 x. right? If we triple it to get it, if we tripled it to make it 2 turn into a 6, then we take 1/3 of it to go back, right? That was okay with you, right? Now, let's look at this. Compare that to this. How about I have a function f of x equals, instead of 3x, 3 raised to the x, right? What does my picture look like? And I'll use the same numbers. Let's go 2 and let's go 3. Let's send those over here through the function. So send those through with f, and what would you get? So the first one, 2, would become 3 to the second power, that's 9. And then 3 to the third power would be what? 27. The question is, can we take them back? Well, we should be able to, right? I mean, seems reasonable or not? This is the question of the day. What's the inverse of an exponential function? What is the function that undoes the exponential function? What would you do if you try division? How would you get from 9 to 2? You see, you can't divide 9 by anything to go back to 2. And you can't divide 27, well, you can divide 27 by 9, but then that wouldn't work for the first one. So, see what I'm saying? You need something that always works. You see the trouble? Okay, so let's try and do it the way that I taught you. How did I teach you to find an inverse? Do you remember this, the steps to find an inverse? If I said, look, take this, find the inverse. What was the first step? Good. Turn it f of x into y. So you would go y equals 3 to the x. Right? And then you're supposed to switch the x and y variables. So everywhere you see a y, you put an x. Everywhere you see an x, you put a y. Do y'all remember that? Okay. So I'll do that right over here. X equals 3 to the y. And then what after you do that? Solve for y. And this is where the walls cave in on us. Because we have no way, have never ever had a way, never done it ever in our lives unless you've done logarithms before. We've never been able to solve an equation where the variable we're trying to solve for is stuck up in an exponent. There's no way to get that variable down. It's kind of trapped up there. Do y'all see that? We can't divide by 3 because this is... Yeah, see, you can't even come in here and say, oh, let me get rid of the 3 and I'll divide, because this is not multiplication between the 3 and the y. So dividing by 3 will not eliminate anything. Does that kind of make sense? Can't root it, because square root won't do anything to the y. Now, if that was 3 squared, yes, a square root would do it. But you couldn't. That's right. Y is our exponent. So do you see we're really stuck? Yes? Okay. Now we are stuck in the sense that algebraically we can't do it. I mean, there's no way we can figure it out, right? We're stuck. But can you tell me, can you look at the 9 again? How can you tell that it came from 2? How are the 2 and the 9 connected? Okay, but just explain to me. The 2 is the exponent of 3, right? So when you say, I'm trying to take 9 back somewhere, right? You're saying you need to take it back to 2, right? So you somehow need to tell me that 9 is equal to 3 squared, right? And that 27 is equal to 3 cubed. And let me put another one over here just so we have one. How about I put 1 in here? Where would 1 go? 3, right? So 3 comes from 3 to the first power, right? So how do you say that? You don't want to say it in a sentence, right? We don't want to sit here and say, oh, that's... So we need a way of saying it without actually having to like write it out in a sentence. Even more condensed, something very simple. And that's what a logarithm is. A logarithm is just a way of saying what we're trying to say in a short, condensed notation. Because there's no algebraic way to say it. Like there's no algebra I can do to get the y out of here. So that's the motivation of a logarithm. It's a way of us kind of rewriting an exponential. So that's just the introduction. Let me now get to what I'm going to define a logarithm now. Logarithm is as follows. We will write log, L-O-G, and then a little subscript b, and then I'm going to put here x equals y. This is the first time a lot of you have ever seen this before. This is called a logarithm. And here's the way you say it first. Like in English, if you were trying to say that equation right there, you would say log base b of x equals y. Log base b of x equals y. So it's almost like you're reading it from the left to the right, right? Log, and then that little subscript b is what we call the base, and then of x equals y. Now what this means, because I mean that's just what it is. Here's what this means. This means that b raised to the y equals x. That's the definition of a logarithm right there. That's the way we're going to define it here in this class. I know it's confusing because it's just like, what? But let me just show you some examples and you'll start to see the connections, hopefully. So how about this? Find log base 2 of 8. What is this? Well, first thing I'm going to do is I'm going to write it as an equation, all right? So I'm going to take this and I'm going to say, all right, well, this means log base 2 of 8 equals something, right? This is equal to something. That's what I'm asking you to tell me, what is log base 2 of 8? Well, it equals something. I'm going to call it y. How about that? That way it looks like that equation up there, doesn't it? Doesn't it look like log base b of x equals y up there now? So I'd like to know what y is. Tell me what y is. Well, what does that up there in black really mean in red? What does it mean? B raised to the y equals x, right? So for us, what's b for us? B is 2. Y is y, right? And x is, for us, what? 8. So could you please rewrite that part right there using the b, the y, and the x that we have? What would it be? 2 to the y equals 8. Right? 2 to the y equals 8. Well, can you look at that and tell me what y is now? It's 3, isn't it? You can look at that now and tell me, hey, look, y has to be 3 because 2 cubed is 8. So y is 3, just by looking. We get that by inspection. Just by looking. So your answer, go back up to this. This equals 3. Let me do another one. Because I know this is confusing first time through. How about log base 3, 27? Yeah, so I'm going to first write this as log base 3, 27 equals y.
So y equals 3.
And now switch it into the other notation. In other words, do that one in red up there, b to the y equals x. What's b for us here? 3 to the y equals 27. Can you tell me what I need to raise 3 to get 27? 3. So the answer here was 3. Y'all see that? We need to do more. What's that say? The loop. I'm going to show you a shortcut trick that I think will help you remember how to do this. We said earlier that when I write down log base b of x equals y, that means what? What did I say that means? B to the y equals x, right? Yes? Now, I use this thing called the loop to help remember this relationship. What you do is you start with the b and you draw a loop that goes to your y and then back to your x. Do y'all see that's kind of like a loop? You see that little loop? And what I'm saying is b raised to that y should equal that x. So if you remember the loop on a log, you can always take the loop and switch it over to this. All right? With me? Do y'all see the relationship? Now, I'm going to separate this page in two parts here. This left side up here, this is called a log expression. Or I'm sorry, let me say log form. And this over here is called exponential form. So what I'm saying by that with these two things is this. If somebody writes something down and it has logs in it, like this over here on the left, you can switch it over to exponential form by using the loop. If somebody gives you something in exponential form, you can always switch it over to something in log form. They can always be manipulated back and forth from one to the other. Okay? Which we'll practice in a moment, but I just want to kind of put that on the page now. Let's go on to another example. What would log base 4 of 2 be? This is tricky. Of what? So, did I hear really what you said? All right. What do we have here? Log base 4 of 2 equals y, right? That's what I want to know. So I'm still going to do that. But instead of going back in my notes and trying to figure out, okay, what was that again? B to the y equals x. Instead of that, I'm just going to do a loop now. My loop's going to be what? 4 raised to the y. So I'm going to write that down. 4 raised to the y equals 2. You see how I'm using that instead of remembering a formula? Oh, no. What the heck is this? What fraction? Half. Why? What's raising something to the half?
Y is lower than
But what does it mean to raise something to the 1/2?
is your decaying,
Not the-
closing. You're making it less.
Remember that the square root of x is the same as x to the 1/2? Isn't raising something to the 1/2 the same as taking the square root of it? Maybe you don't remember that. It's okay. I need to show you a different way, though, okay? Let me show you something. Do you agree right now that 4 is actually 2 squared? So you agree that that's the same problem. 4 to the y equals 2 is the same as 2 squared to the y equals 2. Yeah? Now, do you agree also that if you have something like 2 raised to a power, and then that raised to a power, that you can do something to those 2 in green? What do you do when you have something to a power and then raise that whole thing to a power again? What do you do with those powers? It's either multiply or add. It's anytime it's power to power, it's multiplication. So 2 times y is what? 2y. So do you agree that this is 2 to the 2y must equal 2, right? And what is the power on the 2 on the right side? It's a 1, isn't it? You still following me? Now, if the left side and right side have to be equal, then wouldn't you agree that the 2 powers would have to be equal? Since the bases are exactly the same? If I'm going to say 2 to this is equal to 2 to that, then that means that and that have to be the same. So can you write that down now as a little equation? Forget the 2's down here anymore. This tells me that 2y must equal what? Can you solve that for y? Divide both sides by 2, and you get 1/2. So y is 1/2, which is what we wanted. That seemed odd, kind of weird.
I think Matt just makes your own rules. You can't figure it out, let's make a new rule.
So where to apply this when you find out that the y is 1/2?
What's that?
We should use this when we find out that the y is 1/2.
Well, you should use it anytime you can't just look at it and tell me what the answer is. Like if this would have been the other way around, had it been 2 to the y equals 4, we would have said y is 2 and we're done. But if you can't tell, you're going to have to do some work on it. Okay, let's try another. Because these are just now starting to get fun, right? How about log? Sorry. Log base 2 to the 1/16. Or yeah, log base 2 of 1/16. So the first thing I'm going to do is rewrite it as log base 2 of 1/16 equals y. And I've been using y on the right side, right? It really doesn't matter. I could use anything I want. I could use x, I could use m. Y is just, I needed to do something to give you a general formula, so I used y. Now I'm going to apply the loop. 2 to the y, right? So 2 to the y equals 1/16. Is that okay? If on a test you write down 2y equals 1/16, you'll get almost everything taken off on this problem. It's not 2 times y, it's 2 raised to the y, right? Totally different things. Now, can anybody tell me what power I raised 2 to in order to get 1/16? Well, it may not be obvious, right? What did we do in the last problem when we were kind of stuck? I rewrote that 4 as 2 squared, didn't I? So that I could have both sides have the base 2 in them. Are 2 and the number 16, do they both come from somewhere in common? And think exponential. Don't be thinking multiplication here. They're both powers of what? 2. Do you agree? 16 is 2 times 2 times 2 times 2. It's 2 to the 4th power, isn't it? So would you agree that this equation is 2 to the y equals 1 over 2 to the 4th? Now, anytime I have a power, a fraction like that, with 2 to the 4th, can't I bring that up? Can I bring the 2 to the 4th up? If I wanted to. I mean, we've never really wanted to do this before, but could I bring it up? What would it be if I brought it up? 2 to the negative 4. Do you agree with that? Now do you see that I have 2 to the y equals 2 to the negative 4? Y'all see that? It's okay. That's all right. Well, yeah, because the 2 to the negative 4 is 1/16. That's what it is. So this tells me again, I have the same base on both sides, right? I have 2, 2. I have power, power. Those powers then must be equal to each other. So this tells me that my y must be negative 4. So my answer is negative 4. I'm going to come back to the very beginning and put the answer up here. Let's just think about what this log equation is saying up there. What is that saying? 1/16 equals negative 4. But if I'm trying to explain this to someone who's never seen a log before, what I would tell them right here is this. Look, 2 raised to the negative 4 equals 1/16, right? That's what that says. When I take 2 and I raise it to that power, I get this. I'm not sure I've ever seen y'all so excited. Log base 4 8. I like this problem. See if you can do it. Set it up, let it equal y, do your loop, and then look at that for a second, and then we'll talk about it. I'm just going to write it down while you try it. Is that what you get? 4 to the y equals 8. So the answer is 2? No, it's not 2, right? 4 squared is not 8. 4 squared is 16. So this isn't something you can think of right off the top of your head, right? Now, in the previous problem, what I did was I realized that 16 was a power of 2, didn't I? And I rewrote that 16 as 2 to the 4th. And I moved things around. What's wrong here, though? They're not both powers of 4, but they are both powers of 2. Good. So what about the 4 first? 4 is 2 to the 2nd, and then all of that to the y. But then the right side is 2 to the 3rd. Good. See, 8 wasn't a power of 4. 4 wasn't a power of 8, but they're both powers of 2. So we have to try and find what they have in common. Now, how can I rewrite the left side? 2 to the 2y equals 2 to the 3. Now you have the same you have the same bases, 2 and 2, and then the powers, 2y and 3, so those two must match, right? So that tells me that 2y must equal 3, which means y is 3 over 2. So your answer is 3/2. So the answer to the problem is 3/2. So if you'd like to know what I would have to raise 4 to in order to get 8, I would have to raise 4 to 3/2. And if you don't believe it, what is 3/2? Isn't that 1.5? If you don't believe it, take 4 on your calculator, raise it to the 1.5, and what do you get? You'll get 8. Okay? Last one. That's a 7. So after you do the loop, what does this turn into? Okay, 5 to the y equals 7. Yeah? And, uh-oh. 5's not a power of 7. 7's not a power of 5. They both don't have any common powers, right? They're both prime numbers, so there is no common. So I can't convert it like I've been doing, right? Do y'all see how this is different than the previous ones? So we are officially stuck. And we will be able to solve this, but not today. This was just to show you that there are some logs we still can't do. So it seems like when I was doing these problems, right? When I was giving you these examples, when I was sitting here and I wrote example, I wrote log, I had to come up with a base that I wanted to use first, right? So I would pick a number like 2, and then I'd plug in a number like 4. And that would mean what? 2 to what power is 4? 2. Then I could do another one. Let's say log base 2, how about 8? That would mean 2 to what power gives you 8? 3, right? What would log base 2 of 16 be? 2 to what power is 16? 4, right? Y'all see this? I could do log base 2 of, oh, all right, how about this? 1/2. How about -1? What's 2 to the -1? 1/2. What would log base 2 of 1/4 be? 2 to what power is 1/4? -2. Are y'all kind of seeing this or not? How about log base 2 of 1/8? What would that be? -3. You see how this is kind of working? Every one of these problems, the only thing I was changing was what was in here, right? So like if I plugged in a 4, what came out? Come on, this is the grand finale here. If I plugged in 4, what came out? If I plugged in 8, what came out? If I plugged in 16, what came out? Plugged in 1/2? See? So you could almost look at this log as a function. You plug something in, it spits something out, right? But not only that, it's actually the function that's going to take us backwards from that problem that we had, 3 raised to the x. Remember that, 3 raised to the x? We were trying to figure out a function to take us back, and we got stuck. The log is going to be the one that takes us back. All right, so I need to now define a function. Log functions. A function f of x, which equals log base b of x, is called a log A log or logarithmic, okay? I always use log, but some books they like to say logarithmic. Okay, a log function of base, what do you think? What's my base of that log function right there? B. Just like with the exponential functions, we had base B, right? Here, log functions base B. We have the same restrictions on our base. Our base must be greater than 0, and our base cannot be 1. That was exactly the same with the exponentials, right? We have one other condition with log functions that you did not have with exponential, and that's this. X must be greater than 0. That means what you plug into the log right here. Oh, crap, what happened? That number, you must make sure that that's positive. You cannot plug a negative number or even 0 into a log. It'll freak out. It's kind of like, remember, you couldn't divide by 0? Log functions, you can't do anything but positive numbers. You try something, it'll mess up. All right. This is going to be good. Now, our first example of a log function. F of x equals log. I'm going to pick a base. How about 3? Yeah, we'll do 3. Log base 3 of x. This is the log function of base b, base 3. Let's plug some things in for x. So I'm going to make a t-table over here. Let's plug some things in for x. And what comes out is log base 3 of x. Now, what I plug in, I have to be very careful with. So just watch me first. How about I plug in 3? What's log base 3 of 3? So what this is saying is 3 to what power is 3? 1, right? That's what that means. 3 to what power is 3? So when I plug 3 in, it spits out 1. Okay, how about this? 9. What's log base 3 of 9? 2. Okay, how about 27? What's log base 3 of 27? 3. Right? Now let me try a number that's not a power of 3, just to show you how I had to be careful. How about if I just try to plug in 5? What's log base 3 of 5? So 3 to what power is 5? No idea. And I can't figure it out. I can't write down 5 and 3 as common powers. That make sense? So I can't do that. Right? Can I do fractions? Can I plug in some fractions? How about 1/3? What's log base 3 of 1/3? Come on, we just did this for log base 2. Log base 2 of 1/2 was -1. Log base 3 of 1/3 is also -1. What would be another fraction I could use? 1/9? Because log base 3 of 1/9 would be what? -2. And then what would be another good one I could use? 1/27. That'd be -3. Yes? All right. Make sense or not? All right. Now, I'd like to go back to what we had when I first started talking about logarithms. I had this picture. I think we took the number 2, 1, 2, and 3, and we sent them through this function. The function I had defined was 3 to the x. Remember that? And we said 2 went to 9, 3 went to 27, and we said 1 went to 3, right? And we were trying to find a way backwards to get this f inverse. And we said, what the heck is the inverse of an exponential function? So we needed a function that took 3 back to 1, 9 back to 2, and 27 back to 3. But if you look at what we just did, our function takes 3 where? To 1, 9 to 2, and 27 to 3. So log base 3 is the inverse function of 3 to the x. So what do you think the inverse of 4 to the x would be? Log base 4. And so for every exponential function, whatever base it is, that corresponding log function is its inverse. Yay. All right, so the answer to this question is, it would be this. The inverse function would be log base 3 of x. So now if you took 27 and plugged it in here, right, it would spit back 3. So that 27 goes back to 3. And if you plug the 9 in, it'll go back to 2, and so on and so forth. Make sense? This is what the inverse function is, right here. All right. Still have a few minutes. Let's try and do a graph. Example. Sketch f of x equals, we'll do log base 3x, since that seems to be our fun graph, right? That's the one we've been working on a bit today. So check this out. We could make a t-table, couldn't we? The only thing about the t-table is I have to pick those numbers very carefully, right? The ones I plug in, like 3, 9, 27, 1/3, 1/9, 1/27, right? Things like that. But does anyone remember the relationship between a function and its inverse? See. When it comes to graphs, let's say I'll offer 3 points from your last exam. I'll add 3 points. Who can remember the graphical connection between a function and its inverse? It's okay if no one knows. It's all right.
Isn't it just, is it the opposite?
Yeah, elaborate a little more. What do you mean by opposite?
This means like a reflection of what,
Reflection. What do you? Not parallel. It's some. Not the axis.
reflection of the
Mirror image. Okay, it's all right. Didn't happen today for you. Look, over the identity. But what was it about the x's and the y's? The points. They're switched, right? Do y'all remember that? If I had a function and I wanted to graph its inverse, all I had to do was switch the x's and y's, right? So instead of me coming up with the t-table for this, which makes me have to think real hard about, okay, I have to use powers of 3. Instead, why don't I look at the inverse of this function? What is the inverse of this function? What's the inverse? Oh, in day. What? The inverse of that is f of x equals what? 3 to the x, right? 3 to the x. The inverse of the function of the log base 3 or base 3 function is 3 to the x. Can you make a t-table for 3 to the x easily and quickly? That was your homework assignment, something like that, right? What were the numbers I said to use? -2, -1, 0, 1, 2, right? You plug those in, you get 1/9, 1/3, 1, 3, and 9. Right? So if I want to graph the log function, what I can do is take this t-table and flip it. Switch the x's and y's. So I will plot the points, 1/9, -1, 1/3, -2, 1/3, -1, 1, 0, 3, 1, and 2, 9. Not 2, 9. What am I doing? 9, 2. Flip them. Damn it. Nothing. That's the problem. I forgot my drink today. Okay. Flip the points. Flip the ordered pairs. If you graph that, it should be correct. It should be what we're looking for. You ready to graph it? And we're going to go after this. Now, why am I only drawing the right side? Well, remember I said that x could only be a positive number for a log function? Look at all your x values on those black points right there. All of those numbers are positive, right? 1/9, 1/3, 1, 3, 9. They're all positive numbers. You'll never have a negative number. Let me do that first one. 1/9. Let's say this is 1, 2, 3, 4, 5, 6. 1/9 is just go to the right just a little bit, right? And then go down how much? 2. So it's going to be, I don't know, somewhere around here. Then 1/3, go to the right 1/3 and down 1. And then to the right 1 and then don't go anywhere. Then to the right 3 and up 1. Which puts you here. And then to the right 9, which is off my graph, and up 2. So way out there somewhere. Everyone see these points? Any questions on where they came from? Let me connect these. That's right. Good. I have a vertical instead of a horizontal. Everyone see my vertical asymptote over here? You'll see that? My graph is going to drop down like that. And it goes up to the right. That is our first graph of a log function. And again, want to just point out, the biggest thing here is that to graph a log function, I actually made a t-table for an exponential function and then flipped everything. Now, if you were to have graphed the exponential, right? If I were to have graphed that red one over there, it would have looked like this. It would have been like this, something like that. And that is a reflection over the identity. So here's your homework. Well, you know what? I'll send it to you again. Sorry, I don't want to keep you all here too long. Get out of here. Have a good day. Check your email for your homework.